Welcome back, students. In the previous video, we talked about Maxwell's correction to Ampere's circuitous law. Now the law is called as the Ampere-Maxwell law. Maxwell gave us four equations. The four equations are mathematical representations of the four laws that we already know. And these equations have two line integrals and then two surface integrals. I'm going to write them down so you can look at them and see what I mean. So when we say Maxwell's equations, they are not actually Maxwell's equations. They are, as I said, Faraday's law, and Gauss's law for electricity, and 3, Gauss's law for magnetism, and then the fourth one is Ampere-Maxwell law. This is basically Ampere's circuitous law after Maxwell's correction. So these laws you have already come across in the first 6 lessons of your 12th physics textbook. Now, what Maxwell did was to give them a mathematical form of these laws. Okay, so first, Faraday's law is this: integral, line integral E dot dl is equal to minus d phi b by dt. So Faraday's law. I'll write the fourth law, Ampere's circuitous law. Okay, so now I'll do this number 2, or I should say this is number 2 and this would be 3 and this would be 4. Okay, so I just got the order slightly differently, but you can see that. So number 2 is Ampere-Maxwell law. So that is integral b dot dl. The closed loop integral b dot dl is equal to mu naught into I, the conduction current, plus epsilon naught d phi e by dt. This is Ampere-Maxwell law. And the third law is Gauss' law for electricity. It is the closed surface integral. This is a surface integral. This is a loop integral. This is a closed surface integral of E dot dA is equal to Q enclosed by epsilon naught 0. And then the fourth one is a closed surface integral of B dot dA is equal to 0. So this is Gauss' law for electricity. And this is Gauss' law but magnetism. These four laws, along with the Lorentz force equation, completely describe what we know about electricity and magnetism. Apart from these four laws, all you need to know is the Lorentz force equation. F is equal to QE plus QV cross B, that equation. Okay? If you add that, then all these five equations completely describe electricity and magnetism. You don't need anything else. Okay? I have to say a few things about these laws. Like I say Faraday's law, but you have a different structure here. Okay? What did we see in Faraday's law? We saw this. In Faraday's law, we saw E, which is induced EMF, was equal to minus d phi b by dt. But in place of this E, the induced EMF, we got E dot dl. So what is this? This is field and this is dl, length. How did you get this from here? Well, that is natural if you think about it. So I take a magnet and then I move the magnet up and down. So the flux is changed. So as the flux is changing, what will happen? I can imagine a loop, and in that loop the flux is changing. The flux that is going through that loop, the magnetic flux which is going through the loop is changing. So that is producing an EMF. But what is an EMF? EMF is voltage. Here, how will the voltage even exist without an electric field? So there must be an electric field, and in that loop it must exist. So there must be an E at every point, and then that E dot dl, E dot dl, E dot dl, you know, E dot dl is actually voltage. So we have done that in our previous lessons. When we talked about electric potential, we said V is equal to E dot dl. So the electric field line and the dl vector, these vectors will together give you the electric potential. So you just have to multiply this and then add them together to get the total potential. So we did that in chapter 2. So that's exactly what we're doing. So what we're saying is, as you change the flux, then there will be an EMF induced in that loop, and that would be equal to E dot dl. There will be an E here, E here, E here, E is there. So if I do E dot dl and then if I add it all up, then that must be equal to the potential in that loop. Okay, so that is what we've done. So instead of E, this is what is written as E dot dl. Now it's a closed loop. Okay. So that's what it is. So this is simply this. And what about this? Again, so this is where the contribution from Maxwell. Okay. Changing magnetic field produces an electric field, which means that this, by symmetry, that's how he argued, that change in electric field must produce a magnetic field. Okay, so that is what we saw yesterday. So when the imagined surface was going through the capacitor, there was nothing no current which was flowing across that area, but only the electric flux was changing. So we said the change in flux will produce a magnetic field. The change in electric flux will produce a magnetic field. So this is the second equation. So these are, you can see symmetry. d phi by dt will give you this, and again d phi e by dt gives you B. And this molecular constant. Okay, V naught into I. This doesn't, you see, it is molecular constant. Okay, so basically this change will give me this. This change will give me magnetic field. That's what I said. And then the third is Gauss law for electricity, this you know. But look at, before that, look at this. This is actually a line integral, the closed loop integral, right? Here also. The closed loop integral of an open surface, that's what you said. The surface is open, then you start from one point, when you do Ampere's integral law, then you go all the way and then you come back to it. This closed loop integral, it's a line integral of the open surface. But here, this is a surface integral, it's an area integral. This is a closed surface integral of E dot d. So you hold a charge, okay? And then you imagine a surface around it. Then you do E dot dA at every place on the surface. And for every small area on the surface, you do that, and then you sum it all up, and that must be equal to Q into epsilon naught. You see, it's a surface integral. It's a line integral. It's a surface integral. This is dl and this is dA. This is in meters and this is in meters squared. Okay? So you have two line integrals, E dot dl, B dot dl. And then you have two area integrals, E dot dA, B dot dA. You see how simple it is. In electricity and magnetism, what you have? You have electricity. So you have an electric field. And you have magnetism. So you have magnetic field. E and B. These are the two things in electricity and magnetism. Now you take these two and then do a line integral on both of them, E dot dl and B dot dl. And also do area integral, the surface integral, E dot dA and B dot dA. That's all you do. Those are the four equations. Take E and B, do line integrals on them, and also do area integrals on them. You get 4 Maxwell equations. And we see this minus d phi by dt is what you, rate of change of flux, magnetic flux will give you electric field, and then rate of change of electric flux will give you magnetic field. So there is a symmetry. You change that, you get this. You change this, you get that. So that's what it is. And this, you know, this integral E dot dA is equal to Q enclosed by epsilon naught. The charge Gauss law, charge enclosed surface. It's Gauss law for electricity. And B dot dA clearly is 0. The magnetic flux around a closed surface is always 0. That is Gauss law for magnetism. You may wonder, where is Coulomb's law? You know, we started everything with Coulomb's law. But where is it here? You say, you know, all these 4 laws along with Lorentz force equation covers everything in electricity and magnetism. But then we have not even talked about Coulomb's law. Where did it go? Coulomb's law is Gauss law. Gauss law is Coulomb's law in different forms. They have different makeup. But Gauss law for electricity is the same as Coulomb's law. This law works because Coulomb's law works. Why is this a constant? Q enclosed for epsilon naught. Why is this a constant for any surface in Gauss's law? I can assume any surface, any closed surface. You take a charge, I can assume this, a small volume or a big volume, a bigger radius, a much bigger radius. But if I do this, the flux through it is always same, Q enclosed by epsilon naught. Why is it so? This is because Coulomb's law is working. Coulomb's law is true. You see, what is Coulomb's law? Coulomb's law, for example, if I take this is a charge, and at some distance r, see there's some distance r, okay, I am going to find E. So what is my E is going to be? My E is going to be equal to k cubed by r squared. That's my E. I have r1. Then if I go here, then what happens? And it's going to be k cubed by r2 squared, the distance squared. So as I go further and further and further away, then my field will reduce. Field strength will reduce. But as I go further and further away, what is increasing? Well, if I imagine a sphere, then the surface area increases. How much does it increase? It is proportional to r squared, 4 pi r squared. If I have q here, then if this is r, then if I imagine a surface area, then that is 4 pi r squared. And if it is at some other place, then it is going to be 4 pi bigger r squared. So as my r increases, my surface area is also increasing with the square of r. But what is happening to my field's intensity? If r is increasing, my field is coming down with the square of r, because it is inversely proportional to r squared. So if r increases, my field strength is inversely proportional to r squared. If my r increases, my surface area is directly proportional to r squared. So if I put these two things together, the inversely proportional and directly proportional effects will cancel, and I will have a constant. Right? So that is why this works. This works because Coulomb's law works. This is a consequence of Coulomb's law. So Coulomb's law is already taken care of in Gauss's law. When I say Gauss's law for electricity, I have taken care of Coulomb's law. This is nothing but Coulomb's law. Right? Because E is inversely proportional to r squared. But the surface area is directly proportional to r squared. You know this, right? Because this is equal to k q by r squared. That's why I'm saying this. And this is actually 4 pi r squared. So if you multiply this E and A, then this must be proportional to 1 by r squared into r squared. So this must be, it's a constant, right? EA is always proportional to constant. So then if we remove the constant of proportionality, then I will have some constant. It's always one. It's not, if we put them together, it's always this. That is exactly what is happening here. Okay, so E is kq by r squared, and this is 4 pi r squared. R squared and r squared will cancel. So we will have 4 pi k to q. And that will give you q by epsilon naught, because I am going to expand q here. But that's about it. That's how it is. Okay? So Gauss law for electricity is nothing but Coulomb's law in disguise. So you can say this. This is Faraday's law, this is Ampere-Maxwell law, and this is Coulomb's law, and this is Gauss law for magnetism. Gauss law for magnetism is 0, for closed surface. So these 4 equations are called as Maxwell's equations. And these 4 equations, along with Lorentz force equation, F, I don't have space here. Okay. So Lorentz force equation, if we take that, F is equal to QE plus QV cross B. Add this to this list of 4 equations. So you get 5 equations. They completely describe all that you know about electricity and magnetism. So this is clear to you. Now let's do example problem 8.1. It's a very critical problem. Okay, it's a very important problem. Pay attention to this. If you don't understand this problem, go through it so that you understand it, go deep into it, and if you still don't understand it, you get back to me, and then we'll explain it again. It's a very important problem because if you understand this, then lots of concepts will become very clear to you, and it will be easier for you to do the problems regarding this. Okay. Example 8.1. A parallel plate capacitor with circular plates of radius 1 meter has a capacitance of 1 nanofarad. At t is equal to 0, it is connected for charging in series with a resistor R, which is 1 mega ohm, across a 2 volt battery. Calculate the magnetic field at a point P halfway between the center and the periphery of the plates after T is equal to 10 power minus 3 seconds. The charge on the capacitor at time T is Q of T is equal to CV into 1 minus x to the exponential minus T by tau, where the time constant tau is equal to CR. It's all given. So this is the problem. So you have a parallel plate capacitor doing 8.1. Okay? You have a parallel plate capacitor like this. And this capacitor has circular disc plates, not square or rectangular plates, circular plates, so they're parallel plates. So they are like this. If I look at one plate, then the plate is going to be like this. This is circular. There is one more on the other side. Okay. So this is a parallel plate capacitor. Okay, so the radius is given to be 1 meter. Okay? So this is the center and this is 1 meter. And this is connected to a battery of 2 volts along with another resistor. The resistance value is 1 mega ohms and connected to a 2 volt battery. Now go with the switch here. Okay. Then the capacitance is given to be 1 nanofarad. So this C is equal to 1 nanofarad. Okay. And at any point in time, when you close this, at any point in time, the charge on this capacitor is given by this expression Q is equal to CV into 1 minus e to the power minus t divided by tau. But here the tau is equal to RC. So we take this R and then multiply that with this C, and that will give me the value of tau. So that's a time constant, we call it as a time constant. And then T is a time. It can be 0 seconds, 0.1 second, 0.2 seconds. So as this gets charged, the time will vary, right? So that is a T. But this is a constant, this RC. Okay? So Q at any point in time is given by this expression. This is CV to 1 minus e to the power minus t by RC. So all these are constants except the time. So that gives you, these are all given. Okay? Calculate, what's asked? Calculate the magnetic field at a point P halfway between the center and the periphery of the plates after T is equal to 10 power minus 3 seconds. After 1 millisecond, they want you to find a magnetic field at this point. This is halfway between the center and the periphery. So this is the periphery and this is the center, somewhere here, inside, the middle. Okay? What is the magnetic field? At this point. Okay, so that is what is asked. So obviously as it is getting charged, the current is flowing in it. Till it gets fully charged, the current will flow. As current flows, then there must be a magnetic field around it. And you need to find the magnetic field here. That is what is asked. Okay? So what can you use now? You can use Ampere's circuitry law. Whenever you talk about magnetic field, magnetic field and current, then you have to use Ampere's circuitry law. So for that, what you need to do, you have to imagine an open surface, and then you need to do a closed loop integral around that surface. So B dot dl, closed loop integral of B dot dl around an open surface. This must be equal to mu naught times I. I is a current which is piercing through the surface. That was original Ampere's law. But now Maxwell has modified it. Even if current is not piercing through the surface, if the electric flux through that surface is changing, then that is equivalent to a current. That's what he says. It's what's called as a displacement current. There is no current. Displacement current is not current. But electric flux through that surface is changing. If that is changing, then clearly you can expect to have a magnetic field, a B around it. Change in electric flux will cause a magnetic field, just like current. So it's a current equivalent, a change in magnetic fields. So that's what Maxwell did. Okay, now let me talk about this thing. Okay. So I have two plates, and I want to find B here. Then what would I do? I would imagine a surface. What is a natural surface for me? Usually what we do when we do this integral, we'll try to identify a surface where the B value is constant along the periphery. Why? Because if the B value is constant, then I can take it out of the integration, then do the integration with the rest of the things, because this is constant. So I'll get some value here, and now I can find this value by taking this to the other side of the equation. Then I can find B. Okay? That's the reason why you want to identify a surface where your B remains the same. The same is true with Gauss's law, right? When you apply Gauss's law, what did you do? You found a surface, either a cylinder or a tube. You found a surface where E will remain constant on the surface. So you have to do this integration, E dot dA, right? So if E remains constant, that can be taken out. Then the integral will deal only with the dA part. So do the dA, then add everything, so you get the integration. So then you have taken E out, E, and then this integral value. Now take that value to the other side and you can find E. This is how we apply Gauss's law. Same way, we are applying the Ampere's circuitry law or Ampere-Maxwell law. Okay. So what I'm going to do now? So this is the. So imagine this. I'm going to imagine a circle here. Okay. I'm looking at the circle this way. Okay, but it's actually the circle is like this in between the plates. But as you see, and this is what you see, right? And that is what I draw. This is what I draw. Okay. Again, this looks like a line, but it is actually a circle if you look at it from this side. If you look at it from this side, then it's a circle. But if you look at it from this side, then it is a line. And there are plates, capacitor plates. There is a plate here, and there is a plate there. And like this circle also is centered along the same axis of the plates, the circular plates. The plates have a radius of 1 meter, but this circle, this imaginary surface, has a radius of 0.5 centimeter, 0.5 meters. Because I want to find P there. So here, that's what I want to do. This is my imaginary surface. Does it exist? No. I imagine this. Okay? This is because I want to find B at this point. Okay? So how do I do the integral first? There are two parts to it. The first part is the B dot dl around the closed loop. Okay? So B dot dl around the closed loop. That's what I should do. So that is equal to because around the closed loop, since all these points are equidistant from the center, then I can expect them to have the same B value. Directions could be different, but the magnitude of B must be the same. So I can take it out, and dl is also along the same line as B, so I can take B dl out, right? So this will become simply integral B dl, because dl vector and B vector are in the same direction. B is this way, dl is also that way. So then B dl cos theta will be 1, so B dl is what I get. And what do I know? I know that B is constant at every point, so I can take B out. This is a constant, it's not varying with length. So I can take that out. So that gives me B and then dl. Okay. So if I take dl and if I add all the small dl's around the periphery, then I should get this circumference of the circles, and this must be equal to B into 2 pi r. So this is done. I've imagined a surface which has this point at its periphery, the circumference, in the circular surface, and I've done the closed loop integral of the surface. This is B into 2 pi r. This is done. Okay, now what does Ampere's circular law say? It says that this must be equal, this integral B dot dl must be equal to mu naught into I plus ID. ID is the displacement current. Yeah? I plus ID, and that must be equal to mu naught I, plus this can be written as epsilon naught d phi e by dt. Okay. So this is fantastic. D phi e by dt. Now, let me calculate the amount of electric flux that is going through this surface. So the field, so this is positively charged and this is negatively charged, then there will be E lines there. Right? Now I need to find the amount of flux which is going to go through this surface, through this one. Amount of electric field lines which are going through this surface, and then if I find the rate of change of those electric flux lines, then that should be equal to this idea. Okay? Now, what is the flux, amount of flux lines? Okay. How do I do that? First, you know that in the capacitor, E will be constant, right? So we've done that in the in chapter 2. So you know the value of E inside the capacitor. Inside the capacitor, E is given by sigma by epsilon naught. We know it from our lesson on capacitors. So this is E value, and that E is constant throughout the capacitor, right? Okay. Inside the capacitor. Outside it is 0, you know. Inside it is sigma by epsilon naught. And the area is fixed. The E is constant, and then I can simply take that and multiply that with the area to find the flux. So what's the total flux through this? And the total flux through the entire capacitor would be this E value multiplied by the area of the capacitor. The total flux, I'll call this as phi E or phi total. Okay? Phi total E. This must be equal to E times the entire area of this. So that would be phi into entire area r square. R is this way, 1 meter. Okay, this is r. This is capital R, and this will be small r. This is the radius. Small r is the radius of the imagined circle. The capital R is the radius of the plate. Okay. So this is pi r square. So r is 1 anyway. So I'm going to have this is equal to E into pi. 1 square. So pi E. Okay. So that is a total flux. But am I interested in the total flux? No. I am interested in the flux which is going through my imaginary surface. Either the current should pierce through it or the flux lines should pierce through that surface. Here the current is not piercing through. There is no current flowing between the plates. Only the flux line, the electric field lines are going through. So now, then what is this area? What is the flux here? The flux through the surface, I will call it as phi E. This is phi totally throughout the capacitor. But what is the flux which is going through my imaginary surface? That is phi E. And that is given by this E value into then this area, right? And that would be pi to small r square. And that is what is r? It's 1 by 2 meters, right? So 1 by 2 meters. So it's going to be E into pi will be into pi. And what is this? 1 by 2 whole square. So pi E by 4. That's my pi. Now the question is, what is E? Well, E will be, if you take E and compare, E will be sigma by epsilon naught. But what is sigma? So this is equal to pi to sigma by 4 into epsilon naught. But what is sigma? Sigma is surface charge density. Surface charge density of the capacitor, right? So I should take Q at any point in time, and if I divide that by this area, the area of the plate, then I should get sigma, right? So here my sigma is equal to Q, sigma at any point in time t. Because Q is changing, sigma will also be changing. Okay, because it's charging. But Q at any point in time, let's say sigma at any point in time t, sigma t is charged at any point at that point in time t. So divided by the area, which is nothing but pi capital R squared. So that is simply going to, R is 1 meter, right? So that's going to be Q by pi. So if I take this expression, if I take this value, and if I substitute there, then phi at a particular point in time is equal to phi E is equal to pi into, instead of sigma, I'm going to put Q by pi. Q by pi into 4 epsilon. This will cancel, so I'll get Q by 4 epsilon naught. That's my phi E. So what is this phi E? This phi E is a flux that is going through this surface only. So that is it. Okay, so this is the flux going through this. This is not the total flux, because there is much more going outside of it. I have taken just this flux alone. So that is Q by 4 epsilon naught. But you see, Q is given by this expression. Q at any point in time t is this. So if I do if you want to find the displacement current ID, okay, so displacement current ID, okay, displacement current ID is simply this, right? Epsilon naught d phi e by dt. So that is equal to epsilon naught then d by dt of what phi e? That will be q by 4 pi epsilon naught, right? So 1 by 4 epsilon naught. So for q, I am going to put this. That is going to be Cv into 1 minus e to the power minus t by rc. That's it. Okay. So I can take 1 by 4 epsilon naught out. If I take it out, then this epsilon naught will cancel with this, and I have 1 by 4 d by dt of this Cv to 1 minus 4 minus t by rc. Well, if you differentiate this, this will be gone, because you notice here, this is a constant, this doesn't have any, so okay, I'll expand it, I'll expand it. So this is ID is equal to 1 by 4 into d by dt of, what would this be? Multiply this, Cv minus Cv to e to the power minus t by rc. Okay. So if you differentiate, this is a constant, C is a constant, V is a constant, they are not dependent on time. C is a constant, V is a constant, dependent on time. So if you differentiate it, this will be 0, but this will not be 0, right? So if you differentiate that, then I am going to have 1 by 4 minus Cv is there, and e power minus t by rc into minus 1 by rc. Right? This will come. This constant you will have. E power minus e power ax is equal to e power ax into a. That's what we got here. So this will cancel, c and c will cancel, we have positive, so this will make this equation plus this positive, right? So v by r, okay, 1 by 4 into v by r e to the power minus t by rc. So that's my displacement current. Okay, this is my displacement current. So if I have, now I know V is 2, then R is 1 megaohms, and e to the power minus t is there. R, I have this value, R value is, let's see, RC value, let's see, so, right, RC value. This R is 1 to 10 power 6 megaohms, and then C is 1 into 10 power minus 9, and that gives you 10 power minus 3, that's my true value. RC value is 10 power minus 3. Then what are they asking you to do? They are asking you to find the magnetic field and thereby the current when time is 10 power minus 3 seconds, right? T must be 10 power minus 3. Here T is also 10 power minus 3 and RC is also 10 power minus 3. So this will become 1. Okay? So you see, now ID, this is equal to 1 by 4 into V is 2, yeah, and then this is 10 power 6, R is 10 power 6, and E to the power minus, you see T is 10 power minus 3 seconds is what I said. You need to find that, 10 power minus 3 seconds. And RC, you have calculated the 2 10 power minus 3 here. Okay? So, you see, this will cancel e to the power minus 1. Okay, this will be 2. Okay? So, your ID is equal to 1 by 2 into 10 power 6, then e to the power minus 1. Okay, so that is what it is. Okay, or you can say like 1 by 2 into 10 to the power 6 into E. That's your current. That's the displacement current. And if I calculate this, then I think I get they have not calculated, we just kept it like that. Okay, so they just kept 0.5 into 10 power minus 6 into e to the power minus 1. So they kept it like that. So that's the displacement current I am calculating. But I am not done with it yet. What I found only this. Now I need to equate it with the other things. B into 2 pi r. That will come out. So let's continue now. So what we have done is this. We have found the displacement current ID, which is equal to 1 by 2 into 10 power 6 multiplied by E. Okay, and this is what we have done too. The B dot dl, the integral, the line integral over the imaginary surface is equal to B into 2 pi r. So we came up with this too. Now we need to put these things together in what is called as the Maxwell equation, which is this: B dot dl integral, the closed loop integral B dot dl over this open surface is equal to mu naught times I plus id. I is a current which is piercing through the surface, and id is the displacement current. Now let's look at this area. Is any current piercing through the surface? No, there is no current flowing into the capacitor, so there is no current that is piercing through the surface. So I must be equal to 0. And only id would be present. What is id? That's the displacement current, which is the current equivalent of the rate of change of the electric flux through that area. Okay, so what is this B dot dl? B dot dl, I'm going to have B into 2 pi r is equal to mu naught, and I is 0, there is no current which is piercing through the surface, but then there is this displacement current, which is not current, but the current equivalent of the change in electric field, ID. Okay, so let's put the numbers here. So B, I don't know, that's what I'm trying to figure out. And I want to find B there. So into 2 into pi into, what is R? R is 1 by 2, half meters, right? So that is half meters, half. That is equal to mu naught is 4 pi into 10 to the power minus 7. We know this. And what is ID? ID is this number. So 1 divided by 2 into 10 power 6 into E. Okay? And now, this 2 and this 2 will cancel, this pi and this pi will cancel, then this would be 2, and that's about it. So what is B? B is equal to 2 into 10 power minus 7, then this is going to 10 power 6, I'm going to bring it up, so it's going to be 10 power minus 6. Now what is E? E value is 2.71828, roughly 2.72. So if I do this, what I'm going to get? I'm going to get 2 by 2.7 is 0.74, roughly 0.74, and this will be 10 power minus 7 into 10 power minus 6, that is equal to 10 power minus 13 Tesla. So the magnetic field at this point B is equal to 0.74 into 10 power minus 13 Tesla. So this is how you do this problem. So what we have done is that we have found the magnetic field at this point, even though there is no current flowing through that. Okay? Hope this is clear to you.